Thank you for having me. So, the previous years, I have also been speaking here and talking about factories and the problems that we have putting IT and software on the factory shop floor. This time, I will go one step further and talk about what we accidentally built, basically, to solve this problem. It's also quite a coincidence that what you see here came out of manufacturing, just like what Alan Holler presented before me. So we wanted to deploy IT in factories, which led us quite naturally to peer-to-peer systems due to maximum resilience and minimal infrastructure needs. So we just need Wi-Fi in the end. But as you can imagine, such a system has no central piece. It's really difficult to get a whole world picture that you normally have in a database, so you have no consistency. Which means we need some special kind of support to stay sane while programming these systems. And that's basically, yeah. We ended up, to solve this, we ended up doing what a startup never should be doing, which is create your own database. But it's a very specific one. So, Actyx has been open sourced, so you can try this all out. You can edit the source code, change it to your liking, or open issues, and so on, which will be very welcome. It is all written in Rust, so you typically install it by using cargo install AX, will install the AX binary, which is the main thing. It is both the command line interface and the daemon that you run. AX run starts this process, so that starts your local node of this decentralized peer-to-peer event stream database. Before you can interact with it, these nodes can be remote controlled from the CLI. Oh, this is slightly irritating. So you can connect to them. So you can use the CLI to remote configure and so on. In order to do that, we need some sort of security, and that basically works just like SSH. So the first thing that you need to do is you need to generate your private key for an ED25519 key pair so that you can interact with your node. And then the difference to SSH is the first user that tries to connect to a node will be authorized to configure it. You can see that, so you have AX running in one shell, and then in another shell, you can say AX nodes inspect localhost, and then you will see information about this Actyx node. And the next step that you would then follow is to look at the events API, because that's the whole point. The whole point of it is you can publish an event at one node, and then this will be disseminated across the swarm of devices, whatever purpose you choose, mobile phones, industry gateways, whatever you have, and then you can see these events at any other node in the system. So, when you start AX run, you should expect something like this. This is info level logging that's switched on by default. It tells you which version is running, which IP addresses are bound to where the services are available, and so on. I tried this out at home, I think, and pasted it here. And when you see node started by host, that means it's running. And the last line, node settings at scope, admin authorized users were changed. This was me logging in for the first time and checking the settings. Now, let's do something more interesting with it. Let's say we have two nodes, and we have AX running on both of them. On the first node, we subscribe to an event stream. And these event streams are characterized by tags. When you emit an event, you can attach any number of tags. Tags are just non-empty Unicode strings of your choosing. So here, the tag is my tag. And this subscribes on the local host to anything that carries this my tag. We'll see a bit more complex queries towards the end of the talk. If then at the other node, you say AX events publish, you need to also say localhost. The -J makes the output in JSON format, and this is formatted using JQ here. So we say which tag we want, and then the payload. The payload is anything JSON. This is how you get data into the system and also how it's presented when it comes out. Internally, it's stored as CBOR, but you don't really need to care about that if you're just looking at it from this angle. And what you see here is the publishing has a code, OK, has a result with some data, and these data are just the event key that was assigned to the data as it was put into the system. And you will notice that this event key is the same that is part of the data on the first node. So the Lamport clock is 13, the stream name is this long green thing, the offset in the stream is 13, which tells you there have been at least 12 more events published before it, which have been done by Actyx internally. Yeah, so the tags and the payload, everything comes out. Okay, so this is the basic function of the system. This is all that the Actyx binary does. I mean, it's 250,000 lines of code to basically do this. But, well, it does it without needing any central infrastructure. So it's, you can imagine it like Kafka with infinite retention period, because by default we store forever. And you don't need any central instance. It's just stored on the nodes throughout the cluster and disseminated, and everything just works without needing anything but Wi-Fi between the machines, or Ethernet. Okay, so we come from a factory background. So what do factory people want to do? They don't want to publish events and read them back. That's too low level. They want to model things like this. You don't need to read the actual contents. If you ask someone in a factory to tell you, okay, this is the process that we want to digitalize, we want support from computers in executing this, or we want a computer to actually do this. Like in the left-hand side, we have a logistics order that describes how something gets from A to B inside a factory. How do we tell a logistics robot to do this? So they will start drawing these diagrams. So this expert, the domain expert, will tell you, okay, this is how it works. These are the steps that need to happen. On the right-hand side, this is a small part of a manufacturing process. These two examples are from an actual factory that we are working with, and they are simplified. So the real ones are more complex because these don't show all of the error cases. How do we make this happen? So if we just use these events, it will be very confusing to code. So we really want to use workflows. And that's the main thing that I want to talk about today, which is the library. It's a Node.js library, Actyx Machine Runner. Using this first starts by designing the protocol. We have seen the drawing. Now we need to make a program out of this drawing. So this program starts out by capturing this graph. And it has an initial state, it has transitions into other states, and it might have a final state. I mean, it should have. So we represent this here by having a data structure which has an initial state of name initial. These are all strings here. You will see later why that is enough, because we have some checks to make sure that it actually is correct. And then we have one line for each arrow in the diagram. So from the initial to the requested state, we can go by emitting the requested event. This is the log type. You could also emit multiple events if you wanted. This is done when someone presses the request button or invokes the request command. And to the right here, you see the role. The plant, so we have the problem that we're modeling here is that we have robots and the plants run out of water, and the robots need to go there and water them. So the plant is asking for water, is requesting this watering protocol to be initiated. And then once it's requested, three different things can happen. It can go from requested into the requested, so a self-loop by a robot offering to provide the water, or it can leave the loop by assignment when the plant says, this robot should do it, and then we are in the next state, or the plant may die because the robot has been too slow or something. There was no robot. And then when a robot later looks at it, notices there is no plant anymore that could assign someone, the robot puts it in the failed state, which is also a final state. So we have, this basically came from the domain experts, right? So we know how this robot watering in the garden should happen. Now we need to look into a few more details. So if we look at this line, so from assigned to moving, there is a start command for the robot, which leads to the accepted event being emitted. In the diagram, that means we have a state assigned and an outgoing arrow with the label accepted. This accepted is an event type, and an event type is not just a string. It also carries some data. So in this case, it carries the position of the robot that accepted the watering request. So we're using ZOD here in this example to describe the data type not just as TypeScript types, but also including parsing and formatting facilities. So when you get data from the network, that's valid JSON, you can ask ZOD to parse this to make sure that it actually has a position inside. And this pos data type has X and Y numbers, as you would expect. Now, the accepted value here, so we use machine event design. The type is accepted. This will be a property in the payload that's actually written into Actyx. It will say type : accepted. And it has also the position, which has the pos object. So this is created using this machine event design and gives us this accepted object, which can parse, emit, and so on. And the last one is all the event types that feature in this protocol should be collected in one type, so that we can then give this here to the swarm protocol make. So watering protocol will be the basic tag that's applied to all the events from this protocol, and we know which kind of events can participate. And then TypeScript can tell us when we make mistakes. So this has been the design. Now we need to build machines. And we need to build two machines. We have one for the robots and one for the plants. Each machine can run multiple times because we can have 10 robots and 50 plants. But yeah, so we are looking at the robot here. The watering protocol is used as a factory because this is the robot implementation of the watering protocol, which gives us the robot machine. And now we need to somehow build up this machine. We need to build up the graph. First, we describe the states in which this machine can be. So we design a state assigned. It has some payload data. The payload data is, what do we know in this state? We know the plant ID that wants the water. We know the plant position, so where we need to bring the water. And in the assigned state, we also know the robot ID of who should provide the water. In this state, we can run the accept command, which will emit the accepted event. Now we need to construct the accepted event so that we can put it into Actyx. This is done using this function. The context contains, among other things, this payload data. So we could compose this event, including the plant ID, plant position or so, if we wanted to. And then it gets some arguments. So here I demand an argument of type accepted payload so that I can just put it in here. Yeah, I hope you can all see it. Okay, the third part, so we have the machine itself, we have the states. Now we need to put the arrows between the states. So assigned can react when the accepted event is coming into the moving state. So this is an arrow from assigned to moving by the accepted event. And now we need another function that needs to create the payload data of the moving state. Context contains the payload data of the assigned state, so we can copy what we already know by spreading context.self and then adding the robot position that comes in via the event. Now I told you with all the strings in the first step, it looks a bit stringly typed, and you would be right. But here we have some utilities that make sure that the protocol that you implement is actually correct. So first of all, each of the machines, so the robot machine and the plant machine, can create some data description of this graph. We call it JSON for analysis, because it's passed to another tool that's called machine check, which is written in Rust and compiled to WASM and also usable here. So there's two steps to it. First of all, we check the protocol itself. And the protocol itself might be written incorrectly, so that when not everybody listens to all the events, so somebody might miss some transitions, then the system could get into an inconsistent state. What we want for a factory or for anything else is eventual consistency. We cannot have strict consistency because we want a system that always works, but we want to have at least that when everything is said and done and all the communication has happened, everybody is on the same page. And this is called eventual consistency, or more precisely here we check that eventual consensus will be reached on the transitions that happened in the protocol. There's some theory behind it that I cannot explain in this talk. I talked about that 2 years ago, I think. So check swarm protocol tells you whether your swarm protocol itself is correct. And then the protocol with the subscription is projected for the robot in this case, and the actual robot machine is compared. So this is a comparison between the two graphs, between the two diagrams. And if there is any discrepancy, you will get an error here, so that you know that you have not faithfully implemented the protocol. And then you can fix it, and then everything is fine. But yeah, so there's one thing still missing. So this would be, we have designed it, we have written the machines, now we need to actually run the machines. And we also need to run the machines correctly, as it turns out. So the machine runner has one basically central function, which is create machine runner. It takes a connection to Actyx, represented by an Actyx SDK instance. The tags that are used to identify all the events that belong to this very process. The initial state for the machine, so this is the robot initial, and the payload data that we need to construct the robot's initial state. That one was empty, so here it's undefined. You could also have the mission ID, for example, in the initial state and carry it through if you wanted to. Refined state type is some helper that assigns correct TypeScript types so that you can check your states exhaustively. And that is the reason for that is, this is the main structure for consuming these machines. Who here knows what a for-await loop exactly is? Could I see some show of hands? For-await loop? Yeah, it's a little known feature that is extremely useful, I think. So it's like a for loop, but for an asynchronous generator. Machine is something that you can ask for the next event, and it will give you a promise of the next event. So whenever something comes out, a new state has been computed, a new state comes out, and then you check all the states. So if I'm in this state, I would want to do this. If I'm in that state, I want to do that. And with this refine all state types, you could, in the end, check, ask TypeScript, have I handled all the states? That's the background. Okay, so the state is function also refines the type of the state if it returns true. That's another TypeScript feature that's quite handy. So inside this if block, so when we're in the assigned state, we know that we have this state payload as a reminder. So we can say s.payload.robotID, and we know it is a string. So this is the last thing that you need to know, how to run machines. The state also has a commands object. The commands are the outgoing arrows in the machine diagram that this particular role is allowed to initiate. So the commands it may invoke. And in this case, in this state, the robot can invoke the accept command, which needs the position. There's a second thing here. The machines that I spoke about so far are for workflows that are compact. So they must not have an unbounded number of events, or they should not live for arbitrarily long time periods. There are many things that work like this. So getting things from A to B in a factory is something that takes minutes, and if something goes wrong, it takes hours. So this has some defined life cycle. If you want to have something that lives longer, like a machine in a factory might live 10 years, and it will write a lot of events in the meantime, then putting them into these workflows is inefficient, because calculating the current workflow state means processing all the past events to arrive at the right state. This is the eventual consensus thing. This is where you do it differently for long-lived entities. So the robot publishes with this my tag, this would be the robot tag, and the mission tag, it remembers, hey, I started this mission. And when the robot starts up next time, it can just look for the latest event of this kind and then see, okay, I was on this mission, and now I remember. Yeah, so I was knocked out for a second because my battery was empty, but now I remember. Okay. How am I doing for time, by the way? Should be fine. So, ledgers. All these events have one big advantage, and that was the main reason why we went for an event-driven system. In a factory, it's extremely useful, and it's extremely useful in other places as well, to know what has happened in the past. For one thing, it might be required in some cases to keep an audit log of what has transpired, but also it has helped us a great deal debugging application problems of all kinds, usage problems and so on, using the event log, because we could see exactly which buttons people had pressed on the tablet and then found out, okay, this was a bug on our side, or no, you pressed the wrong button there, and it was very easy to figure out, because everything is in the log. This is also a reason why these events need to be human readable. So we went not with some magic approach like CRDTs, where you can publish some operational updates, and they achieve a similar goal, and they also achieve eventual consensus. But the updates are not human readable. So we wanted things to be human readable. We want to talk with the people who design the actual workflow, and they are the domain experts that tell us which kind of states they're in and what the events mean and so on. So this is why we chose this. And naturally, you can look at that also in Actyx. I mean, otherwise I would call it a PubSub broker, but this is why I think it might be adequate to call it an event stream database. You can actually look into it. So here I show you an example of trying to figure out all the watering protocols and whether they have been completed. We look for a combination of tags, so something that has the watering protocol tag and the water request tag. This is added to the requested event that the plant writes. And then also we put a restriction here that the time is after 1 day ago, so only from the last 24 hours. Now, there's a let binding in the next line with a subquery. So for this watering protocol request that we see, in the first event, there is this property called request ID. Now I can extract that and use string interpolation to create a new tag, namely watering protocol colon and this, which is the mission, basically. It's the request ID. So I see everything that happened during this mission. And then I filter that on the type field, and there is the last event that says done. When the machine has provided the water it emits this. So this one, completed, will return an array of matching events. There should be 0 or 1 of them. The machine writes the done or it doesn't, essentially. So the last step is to assemble the object that we want to compute. Namely, we take requested as the time of, so there's this underscore between the parentheses, which means the current event. It's the watering request. So the time of the watering request. Time also returns an array because the number 1 does not have a time. A single event has 1 time, namely when it was written. And if you compute a result from multiple events, you get 2 times, the minimum and the maximum. So the requested, there is just 1, so we take it out. And for completed, we try to do the same thing, but there might not be a completed event. So this is why this question mark is the null-ish coalescing operator in JavaScript. I basically took the same syntax for the same purpose. So if there is no time of the 0 index, then use null. And you have probably read the result by now. So I had, in this case, I had 4 missions that were never completed, and then I have 3 missions that were completed. So you can imagine that you can do all sorts of query with this kind of infrastructure. So yeah, this brings me to the conclusion of my talk. We have AX Run that provides a decentralized event stream database for tagged event streams. We have the rest of AX, which is the CLI for interacting with a running AX run. We have the machine runner library that makes it possible to write reasonable programs on top of this. And we have the Actyx query language to look into these event streams and figure out what has been going on in the past and troubleshoot and do business intelligence and process optimization, mining, and machine learning and whatever you want. Okay, so main website is developer.actyx.com, and everything is open source under the Actyx organization on GitHub. Thank you.